Hello everyone, I'm super thrilled to be here and I would love to share with you the really exciting world of machine learning. So today I will attempt to demystify machine learning and try to make it a little bit more understandable and less like magic, and then a couple of steps about how you can get started today. So I'm Boris Yakubchik. I am from Forbes, really proud to be working there. We have a wonderful data science team with an excellent mentor who's helping me learn a lot of this stuff. So let's take a look. Outline, I'll talk about machine learning. I'll show you a lot of examples. We'll look inside what a neural network is, roughly. We'll do some image recognition, and then I'll show you some code. I will post these slides online, so don't worry if I'm going through this really quickly. I have something like 40 slides to show, so we're going to run. This is, I think, a kind of cool quote. Any sufficiently advanced technology is indistinguishable from magic. I don't know, but, but I hope that by the end of this talk you will not think that machine learning is magic and that really you are capable of understanding it. It's just a matter of kind of learning a little bit more about the details inside. So machine learning is broadly a large set of mathematical approaches to creating models that can predict outputs based on inputs. And there are very many different things that machine learning can do. This little picture on the side kind of shows you there's lots of little avenues, and they're in some ways a little different from each other. But today, we're going to be talking about supervised deep learning. Supervised because we actually know what the labels are for the data that we have. We have an example, and then we say the correct answer is this. So is this a picture of a cat? This is a picture of a cat. You know. What is this a picture of? It's a dog. We have labels, and so it's supervised learning. We're teaching the computer what the right answers are. And it's called deep learning because there's a subset of machine learning called deep learning, and it is just a set of techniques. Okay, so first I'm going to go through a lot of examples. Perhaps you've been following machine learning and you know what it's capable of doing, or perhaps you haven't, so just a little brief overview. One thing is called style transfer, where you can teach the machine to recognize a certain style and then apply that style. You can make a picture look like Van Gogh painted it, and you can do that for every single frame of a movie, and then you can have a movie as if it was painted by Van Gogh. You can switch zebras to horses and back, and of course more interesting things, and it's up to you to just train the model and get it to work. You can colorize images, so you can give it a sketch, you can give it a reference picture and say, make it look like this, and in seconds you get a cool output. Pretty amazing. There's something called YOLO, you only look once. It is a really, really fast approach to identifying objects. It can happen real time in relatively non-powerful hardware. So you can just have a web camera that'll automatically detect anything that's scrolling through. We can do better than just image detection. We can segment and outline the objects in the picture and then label them and say, this is a person, this is a person. You can take an aerial photo, well, semi-aerial photo maybe, and then say, how many sheep are in this picture? Well, 57. Machine can do that. There's something new called Denspose. It comes from Facebook, and what you do is you provide it with a picture, or of course video sequence of images, and it will overlay a 3D model of people over the image. So you can recognize the pose that the person is in, and maybe do some cool stuff with that. Image to sentence, you can take an image, translate it to a sensible sentence. Here, a boy is doing a backflip on a wakeboard. Yeah, pretty accurate. It's a backflip, but I mean, it's a trampoline, but whatever. This guy on Twitter is doing really cool stuff. This is just one example. He has trained a model on Renaissance paintings, and so now you can just have anything look like a master painter has done it. I particularly like this example on the right. Okay. We can make waifus, generate thousands and thousands of unique characters which look quite realistic, or you can get real-life people. So there are advanced techniques that will generate high-resolution, very photorealistic images. There's something called deep fake, and you can swap faces, and you can change any face to any face, and you can do that very realistically, and you can get some awesome results. That's or one overlord Nicolas Cage. Okay, So there's going to be a lot of vocabulary. You don't have to know this vocabulary, but over time you'll kind of begin to pick it up, and it's helpful to know what these concepts are, even if you don't remember the word itself. We'll talk specifically about dense neural networks. So neural networks are these mathematical structures that are just composed of layers. Here, looking from left to right, we have an input layer, some hidden layers, or you should think of them as processing layers. They're not hidden, we can see them. They're processing layers, and then we have output layer at the end. So you feed some input, the machine does some prediction, and then gives you an output. And it's called dense because every piece, every layer is connected to the previous layer and to the next layer in all ways. It's not the only architecture, but this is a common one. And it's a very simple one to understand, so we'll go through an example like it. So let's say you have a simple data set. You have X and Y component, and based on those two, you have an output, either an O or an X. So it's a classification problem based on input. So we're going to train a model. A model is what we call the computer code that's going to be doing the predicting. So we have input and output, and here we have labeled data. Your input maybe is a coordinate 9,8 or 1,2, and you get a correct output. And what we will do is we'll try to train this model. And all you as a programmer have to do is basically set the hyperparameters. Hyperparameters are basically things about the model that you define. So the number of layers, the way that they're connected, there's something called activation function and other stuff. But basically, you're just talking about the features of this model. You write it in code, and if you're using Keras, it looks that simple. You basically say, hey, Keras, what I want is a model that's sequential, one after the other. Hey, Keras, let's add a layer. It's going to be a dense layer. Hey, let's add another layer, another layer, another layer. Let's compile the model, and then fit, that is, train the model. So this is actual code that will run. That's all you need as long as you provide the input and the correct labels. So that model right there is just this tiny bit of code, and what you do is you tell it to train, and within seconds you're done. Machine learning is over. It really is magical when you look at it from the outside. But of course we're going to look under the hood. So how does it work? Okay, here's what the computer did. And I'm going to do hand waving. This isn't exactly what it does. Maybe it's not the right stuff, but metaphorically this is the right idea. Here's what it does. It sets up exactly the layers and neurons that you told it to, and then it fills it in with random weights. Your model needs to be initialized with some randomness, so it does that. And then we start feeding the input. We give it one example, and all this thing does is some computation. And the computation is relatively straightforward. Take the input, multiply it by the random weights, add it together, and just pass it on through. And every single neuron is going to do this procedure. It's going to multiply, add, and over time, at the end, once you get to the end, you get an output. So not really all that magical, it's just simple math. Multiply, add, some fancy activation function. Okay, so the output is going to be some number. Here we have two outputs, and it's basically saying, ooh, it's not exactly probability, but let's call it that. Probability that it's an X is 60%, and it's an O with 40%. So the model thinks, well, 60 is bigger than 40, X is the correct answer. Let's see, is that true? Yes, that was the correct answer. So now what the model does is it computes loss. Loss is basically the error. How far off was your model when it made that prediction? Well, it thought that the correct answer was 60% accurate, but really the correct answer is 100%, it's an X. So the loss is how far away was your prediction from the actual answer, in this case, 0.4. Now, it's not always a subtraction. Sometimes you subtract and square and do some other stuff, but the basic idea is you're computing loss, you're computing how far away you are from the correct, and you want to decrease loss. They call it gradient descent. But anyway, you want to decrease loss, and the way you do that is back propagation. And this, in some sense, is what's at heart of machine learning. This is, well, deep learning. This is the cool thing that makes the whole thing work. Metaphorically speaking, we say, hey, this number really should be higher. All those random weights, maybe if we just tweak them a little bit, that final answer would be higher. So how do we do that? We kind of feed back, we propagate the answer back, we say, hey, whoever told me this was wrong, this was supposed to be higher, increase that. And whoever told me it should be lower, decrease that. So the machine learning algorithm is going to tweak the weights a little bit to make sure that when the same input is given, the output is going to be higher than 0.6. So you're going to decrease loss. You're going to get more accurate result. Well, of course, you now have to do that for the full batch. Batch is basically a hyperparameter. It's how much data you provide to the model for it to do the learning before it actually updates the weights. So let's say the batch is 5. You give it 5 pieces of data. It keeps score of what it needs to change. At the end of the batch, it updates all the weights, and then you continue training. Now, you continue training, well, you update the weights, and you continue training until a full epoch. That's the fancy word for when the model has seen all of your data. It's seen 100% of the data, and then it's going to do it again, and again, and again, until the end condition, which could be the user stops it, or you can just say, once I reach an accuracy of 90%, stop, whatever you want. So that's it. You just do this over and over and over again. You do this back propagation, and it works. Now, with that in mind, I think this example will be a little easier to understand what's happening. This is a fantastic visual simulation online that you can play with. What you do is you can set up how many hidden layers you have, how many neurons you have, and the data here is a little more complicated. You see the orange dots are in a circle, blue dots in here. The setup is the same: 2 input, 2 output, 3 hidden layers, 3 neurons per layer, 2 layers. Let's run it. And in 74 epochs, that is 74 times that this model has seen the entirety of the data, it has learned that the correct judgment is blue when it's roughly in this region and orange otherwise. So these things are super quick at learning non-trivial data, right? It's not just a linear regression. We're talking about setting a region. This is in 2 dimensions, but it doesn't have to be limited to that. It could be 3, 4, 5, 100, 1,000 dimensions. It doesn't matter. You make a more complicated model, and it'll work, usually. So your task as a developer, as a data scientist, is basically play around with these models, try different architectures, and see if you get good results. Ta-da! Okay. So now, let's move on to image recognition. Image recognition is done typically with convolutional neural networks. It's a slightly different architecture, but it's the basic same idea. A convolution is a mathematical operation that simply takes in this case, a 2-dimensional image, a bunch of numbers, and tries to summarize it. So you have a certain region, and you're going to summarize that region into a single number. And you're going to do that for every single sub-region, and you now get a new image, a new matrix, basically. And you can do that again and again and again. And what that allows you to do is to summarize regional data. Maybe you recognize there's an eyeball here. Maybe you recognize there's a nose here. And once you realize that there are eyeballs and noses nearby, maybe it's a face. So you can detect higher level features as you work your way down this model. So typically, convolutions will work like this. You take your image, you convert it to numbers, you feed the numbers into a convolutional network. It starts compressing it down into smaller and smaller and smaller images, although they're no longer images, they're kind of abstract representations of the image. And now you can also see the depth is getting bigger because you're kind of keeping track of more and more features. And in the end, often what you'll do is you'll unwrap that, you'll flatten it, and make a dense neural network, connect it all, and then at the end you'll have a classifier. Backpropagation works the same way. Right now, let's say the model predicts bicycle, you say wrong, and you start working your way back, updating the weights so that next time it will be more likely that it'll predict car. Okay, so visually it looks kind of like this, and the architecture can be a lot more complicated with lots of little pieces, but typically in convolutional networks, what you'll have is low-level features being detected early on. Maybe edges, parallel lines, vertical lines, horizontal lines. Later down, those features are going to be picked up and understood in a more abstract way. Maybe when you have horizontals and verticals nearby in a circle shape, it'll say, ooh, that's a circle-like thing. So in the middle, you might be getting abstract textures, and these textures may be maybe slightly correspond to feathers in some ways. Maybe some textures will maybe correspond to metallic-like objects. It's not like a clear one-to-one correspondence to our language, but for the machine, it's able to then combine them into even more abstract, weird things, and then make amazingly accurate predictions. And so you'll see an example soon. Okay, and now there's a cool visual thing online. I really want you to see it. Basically, you draw something like a 7, and then it is a convolutional neural network, so it breaks it up into pieces, figures out features, and then on top at the end, unwraps it into a dense neural network. And you can see there's no way for a human maybe to understand what these dots represent, but the machine has trained itself and knows what to do, and correct answer is 7. Let's see, clear it out, let's do something like a 6, ugly 6, it's thinking maybe it's a 5 or a 6 or a 7. So these things are really accurate, really fast, it's exciting. So how to get started today? It's so easy. First of all, I really recommend Keras. Lots of people recommend it. If you're trying to play around with machine learning and you don't want to learn all the really dense details of all the fine implementations, use Keras. It's like Lego pieces. You saw the code, just put one thing on top of another. It's a beautiful API that is really easy to play with. Now, the author of Keras, Francois Chollet, also wrote a book called Deep Learning with Python, and this is the primary source of my knowledge at the moment. I mean, I've read online as well, but you really want to learn from a textbook where the thoughts are clearly organized and laid out, and this gives you a beautiful introduction to machine learning and goes through Keras and how to use it in a wide variety of architectures and problems to solve. So setting up your environment is pretty easy. Install Python 3.6 or above. Install pip, which is a package manager, kind of like NPM for JavaScript. Install virtual environment, venv. It's a way for you to say, in this folder, this is the kind of Python packages that I want to use. You can make some aliases so that it's easier to work with. You go to your directory, you create, this is the command you'll need, you want to create a virtual environment, folder called virtual environment, or any other folder names, just may as well call it venv. And then you are going to activate that environment so that once in your terminal you type any command, it will use those Python packages. I have an alias, so I just say activate, it's easier. On PC it's a little different. And finally install the dependencies, pip install requirements, and you're done. The requirement file looks like this. Basically, you'll want to say Keras, TensorFlow, a couple of other things. I can just copy paste this one. Some of them are exact versions if you prefer, so it doesn't matter. I have a repository, I'll share that one too. Really easy to get started. Okay, and when you're playing with Python, you could write all the scripts in your editor and then run the script and not like it and then go back and have to do it again. Or you can use Jupyter Notebook or Jupyter Lab. The lab is the successor. It's a little bit better in some ways. So you have bits of code that you can run and rerun in whatever order you want. So if you have a lot of processing to do, you can do that once and then just play with that data without having to reprocess it every time you run your script. It's beautiful, gives you visual output right away. You can show how well the model is doing. In this case, the accuracy is going up, loss is going down. It's a success. So what can you do with it? Well, now there's Tensorflow JS, which is a JavaScript kind of wrapper, I don't know, whatever. It's a thingy that lets you use machine learning in the web. And it allows you to use existing models. So you could train something in Python, and then you are going to be able to provide it to the user, and then the user will be able to use the model. You can even retrain it. So often with these image recognition systems, you can have a very good image recognizer, but you don't want to recognize whether it's a dog or a cat. You want to recognize features that the user is showing. So what you'll do is you'll train your own classifier, and that's something you can do even in JavaScript. So there's a demo with Tensorflow JS where you can train it in a few seconds to play Pong with just 4 different images. So when you hold one object, it'll go left. When you hold another object, it'll go right. Or you can just do it with your face, look up, it'll do that. Fun stuff. Okay, finally, I think this is kind of like cool new stuff that I haven't really seen done, but I imagine it's pretty straightforward. Electron is basically Chrome and Node.js. So you've got web technology in your browser, but it's wrapped in a way that is packageable and exportable to Mac, Windows, Linux, and some of your favorite apps that you use were written in Electron. So you can make a thing that people can use on any operating system by simply taking TensorFlow, putting it into a browser, putting the browser into your Electron, and off you go. So I think that's really cool. So all of you get a machine learning. It's going to be great. And live code. You have a minute? We have a minute? Please, yes, thank you. Okay, so fun times. We're going to go to my light. Darker? Oh, you don't have to see anything in here, don't worry. All I'm going to do is do activate, which is my cool virtual environment alias. And then I'm going to do Jupyter Lab. Ta-da! Now we're running Jupyter. Jupyter is so sweet. We're going to go to, loading. Okay. I've not seen that. What? Something, you know what? What a crazy live demo. Okay, I'm going to use a different terminal. I really wanted to show that terminal. It's really cool. CD, desktop, Keras, machine learning, activate, and Jupyter. Something must have broken. Okay. I'm going to use Jupyter Notebook. It's a slightly older version. It'll work the same. Okay, so we go to Notebooks, and I have my image recognition. That's the thing that I wanted to show you. So all this code is running in the browser, but there's a Python backend, and you can run things in different order. So we're going to run this bit of code, which basically imports what we want. We are going to use the Inception 3 image recognition model that is available for free. It's a very powerful model. And this one is about 90 megabytes. You don't want to train this kind of thing. It takes you a long, long time. But you can just use somebody else's existing model. It takes a while to load, so it's almost done loading. Little start. Sure. Thank you. We can show the model. Now, I just want to show you, this model is super duper large. You can see how many layers it has. All these are layers, and they're all convolutions and batch normalization, whatever else. And in the end, you have 23 million parameters. So those random weights originally that were initiated had to be then fine-tuned to be able to recognize 1,000 different images. So training 23 million parameters and tweaking them is a time-consuming task. You don't want to do that. So you wouldn't want to train this from scratch. If you want to retrain it, you would just take off the head, remove the last bits and pieces of it, this stuff at the end, and then train your own. Okay, so I have a couple of images, basically panda, cat, dog, bunny. We're going to choose panda this time. You load up the image, and you have to process it a little bit. Basically, the image needs to be converted to numbers because that's the way the model understands it. In this particular case, what we do is we, first of all, resize it to 150 by 150 pixels, and then we convert it to an array of arrays, and each one is going to be looking like this. You see just 3 RGB values, and they have to be between 0 and 1. That's just normalized for this particular model. So then later, we're going to make a prediction. All you say is, hey, model, let's predict my image. And it takes a second. Now it has a prediction. Prediction looks like this. It's kind of useless. But what you can then do is just decode predictions. This is a feature of Keras. So Keras makes it really, really easy to work with things, like I said. So you just say, hey, decode predictions. I'm sorry, this is a previous output. That's why it's there. When I run it, it'll update it. There we go. Oh. Okay, so it thought that it was a giant panda. Let me show you what it looks like. Carrots, images, and panda. That's what the panda looked like, kind of small. Let's give it a cat. 1 second. So I'm just showing you, you can reuse the code without having to re-import the library. Cat is number 1. So all we need to do is rerun this piece, rerun the import image, rerun the conversion. We don't need to look at the shape or anything. We just need to make the prediction. And then we go back to decode prediction. Let's run it, and hey, it thinks it might be an Angora or a wallaby or an Egyptian cat. Let's see what the cat looks like. Cat. Good enough for now. So I just wanted to communicate that with Keras, machine learning becomes a joy, and it's really, really easy. Machine learning isn't really complicated. All of you are fully capable of doing it. It will take a little bit of time, and it really helps to have a very good introduction. So, Python with, oh my goodness, yeah, there we go, that guy. It's a pretty cool start. So thank you very much, and I'll take some questions.
So, 2 questions, and someone asks a question.
Yeah, so the question is roughly about how much time might it take to train these larger models, image recognition or something, and maybe you don't have a very powerful computer, so you might need to borrow some servers online. I haven't dealt with servers online. I mean, I get it. You just pay some money and you do it. Having a video card will be, well, a particular video card. Typically, the CUDA processors in NVIDIA video cards is what really does well with some of these mathematical operations. For certain kind of training, like deep models, it might be fine to use a CPU, especially depending on the size of it. And you actually can do image, like really rudimentary image recognition with just deep models. They're just not very, very good. Convolutions are much better on a GPU, and they will run as much as 10 times faster, I think, than on this machine. So there's one example which I have from this book, which trains your own cat or dog recognizer. And it's a really dumb image model in that it can only do 2 things, cat or dog. You give it a hedgehog, it'll still say cat or dog. But that one takes maybe 5 minutes to train on this machine, and the accuracy is pretty good, 80, 90%. On my GPU at home, when I ran on the computer, I think it was like 30 seconds, or I don't remember. It's much, much faster. So if you're training something relatively narrow focused, I think you can do it quite fast. And with a typical computer, if you're trying to do something more broad, you might have to venture outside of that. Not quite sure, but you can definitely play with it. Like this computer is good enough. Other questions? Yes. Excellent. So the question is, does Keras have a way to, like, tools for cleaning data and, yeah. So one big thing that will take you a lot of time is cleaning your data. So depending on the data set you have, you will have to learn a lot of skills about how to fit this thing into this magic box. And it's not impossible, it's a skill set of its own, and that I didn't cover at all in here. There is something called Kaggle competitions, and there are many different actual live, real-life data that you can get to play with. And there are many people who have worked through these data sets and shared their approaches for solving these problems. And the simple kind of intro-level one that they recommend is the Titanic data set. So I think it took me like 10 hours to try to get this simple data about what the age of the person is and what the other stuff into a model. And the model took me about, I don't know, 5-10 minutes to write and took about 1 minute to train, and I got cool predictions like 60-70% prediction just like that. So I spent most of my time just trying to convert the data. Now Keras does have some things like one-hot encoding, haven't talked about it today, but it's just a way to take data and make it into a vector where you have mostly zeros and ones in certain places. So there are tools like that. There are other libraries that will allow you to do that. I think sklearn is one. It's kind of a skill set of its own, and you'll need to spend some time on it. But it's doable. It's all right. Yes. Oh, thank you for that question. So the question is roughly about what to do once you are graduating out of the beginner stage and you're thinking about what to do intermediately. I am personally sort of in that category at this time. I'm no expert. I think there are some excellent courses out there. I think there's fast.ai, which is supposed to be a really quick and straightforward way of learning kind of a lot about machine learning. There are excellent free courses online that are taught by some of the experts in the field, Andrew Ng, for example. For I'm still trying to pick a good course to follow. I think a good textbook is excellent, like the one that I'm recommending. And as for courses, I remember Andrew Ng in one of his introductions was saying that try out different models. So you hear about something, like somebody did this kind of setup for trying to predict certain kind of thing, see if you can build it. And the more experience you have in building these things, I'm guessing the better you're going to get at it. I was struggling for a while with Titanic. At some point, I just gave up and said, okay, I'm not going to encode any of these numbers. I'm just going to literally feed them, whatever it's 1, 2, 3, who cares, just feed it into the model. And it worked, and it was fine. But then later, as I learned a little bit more, I figured out a way to split the model into categorical data, one which is completely discrete. The person, how many family members they have on board. It's a discrete number. It doesn't make sense to have 3.5 people. And then numerical data is separate. So what it is, I split it up, and I have a piece of the model working with numerical data, piece of the model working with categorical data, and then marrying the two pieces together to give you one output. And you get slightly better predictions. But I think just working on implementing different models may be a good way forward. But I'm just kind of early stages of intermediate, so I don't know if I have good advice. Well, thank you so much.